So I'm being asked about number 15, 16, 17 from the homework, but I can't do them all right now. To estimate the number of trout in Big Bear Lake, it's a good lake, a sample of 48 were captured and tagged. After releasing them, a net captured 300 trout, of which 9 were tagged. What would be a good estimate for the number of trout in Big Bear Lake? Okay. So I'm going to draw a picture. Here's the lake. It's got all the trout in there, right? How many trout are in there? We have no idea, right? So why don't we just say capital T, let's say, is the number of trout that are in the lake. T equals number trout. That's what we'd like to know, right? That's what we'd like to know. Now, we captured how many of them? 48 of them were captured and tagged. So how many, proportionally speaking, what is the proportion of the trout that are tagged to the number that? No, look, you have, okay, if there are 8 women in here out of 22, what's the ratio of women to the class? 8 out of 22, right? 8 divided by 22. The ratio, 8 to 22, yes? So what I'm trying to set up here is a ratio of the tagged to the total number of trout. What's the ratio of the tagged to the total number? How many are tagged? 48 out of how many? How many trout are there? We don't know. Call it T. Do you agree that that's the proportion of the tag to the total number? Yes? Okay. Then they captured 300. And 9 of them were tagged. So that is a good estimate for the proportion that are tagged versus how many are in there. Does that make sense? They're going in here and they are taking a sample out of here of 300. Turns out that 9 of them were tagged. So that it's not perfect, but that should be able to give us an estimate out of the correct proportion. This proportion should be the same as the, 9 out of 300. Does that make any sense at all? Okay. Now, it's an estimate, though, okay? It's an estimate. It's not perfect. It's kind of like if I'm so bad at analogies. If everyone here, I gave everybody a special pencil, okay? So there are, let's say 22 people in here. Out of everyone on campus has a special pencil. And then everyone leaves here, and then I go out and I take a sample of 100 people, and 2 of them had the special pencils. Then that kind of gives me a proportion of, I can somehow figure out how many people are in total on campus. It's an estimate. I don't know if that makes sense. That just confused you more. Can you solve this for T? So you do the cross multiply thing. So when you multiply here, you get something. Here, you get 9T. What's the 48 times the 300? What is it? 14? Oh, 400. Divide both sides by 9, and what did you get? 1,600. It's T. That's my estimate for the number of trout in the lake. I mean, it could be, you could argue against this pretty easily because you could be like, okay, any trout that were caught initially and tagged have learned to stay away from nets now. So I mean, It's not perfect, but it's an estimate. All right, 17, you want me to talk about that one? All right, is that IA? Or is that 1? I don't know what the hell that is. Yeah, I think so. A team of college administrators captured and tagged a group of 90 fraternity men and then returned them to the campus. Later, a group of sorority women wishing to estimate the number of fraternity men on campus captured 245 men, found that 35 of them were tagged. This is exactly the same thing, right? So 90 fraternity men were tagged initially out of the total, right, number of fraternity men. Then the sorority women went out there, captured 245 of them. 35 of them out of the 245 were tagged. And so you set up the same thing, do your cross multiply. Okay, then I'll talk about 15. Did you get 630 for this? 630 is what you should get. Fraternity men. The T up there was trout. This would be fraternity men. All right, you want 16? 15, sorry. At a certain animal shelter, the ratio of puppies to adult dogs is 7 to 4. You have 7 puppies to every 4 adults. That's probably not right. Right? Most people want to adopt the puppies. You would think you would have less puppies, but who cares? This week, there are a total of 55 dogs in the shelter. How many puppies are there in the shelter? How many adult dogs? So this one's a little more confusing. So again, you know, draw a picture if it helps you. Here's the shelter, right? Inside the shelter you have what? Puppies and adults. Yes? We know that the ratio of puppies to adults is always 7 over 4, or appears to be 7 over 4. Agreed? Here we have 2 different letters. We can't solve for a single one because we have the other one there also, right? You'll follow that? Okay. So let me try and put this 55 into perspective. If there are 55 dogs, we could have what? 10 adults and 45 puppies, right? That's one way you could have it. You could have 10 adults, 45 puppies. But would that maintain the ratio of 7 to 4? No, it wouldn't, right? It wouldn't. What we need is that the ratio of puppies to adults is equal to 7 over 4, but at the same time, what? They have to add up to be what? 55, right? So the key to this problem is to understand that this is the ratio you want to solve, right? You want to solve for the number of puppies or the number of adults, but you have to use some other piece of information to try and simplify the problem. So because of space, I'll erase this. The other given information is that puppies plus adults must be equal to 55. Now what we have here are 2 equations, right? We have an equation that relates the puppies divided by adults, that must be 7 over 4. And then we have that the puppies plus adults has to be 55. If I'm trying to solve for a single letter, and I have 2 equations, what I can do is solve one of these equations for either A or P and plug it into the other equation. All right, so which of these would you like to solve for? Would you like to figure out what P is here and plug it in here, or would you like to solve for P here and plug it in there? It doesn't matter which way you go. Or do you just want to see me do it for the first time? Okay. All right, so I'm just going to choose to come over here and say that P is equal to 55 minus A. So what did I do to get to this? Subtracted A on both sides. Now, I don't know what P is because I don't know what A is, right? Can't tell you what P is if I don't know A. But if P has to be 55 over A, come back to this equation and rewrite it. And let's forget the puppies and adults for now. Let's just write 7 over 4 must be equal to, what's P though? It's not just P. It's 55 minus A over, what's this equation? It was P over A, right? So I put A here. Do you see what I've done? I've replaced the P here with how I know it's connected to A. It's whatever 55 minus A is. That's how many puppies I'll have. Do you follow? Now, here you have now just one equation, but how many variables do you have in here? One variable. It appears twice, but there's just one variable. So we should be able to solve for it. Do your cross multiply again. What's A times 7? 7A. I'll move this over here. So the left side becomes 7A equals, now be careful on the right side. You're going to multiply 4 times this, right? That means the 4 has to go to both. So I think I'll write it down. 4 times 55 minus A. Distribute the 4 through. So what's 4? What do you have? Oh, I thought you said 320. I'm sorry. 7A equals 320. 220. I thought you said 320. Minus what? 4A. And what we've done is we've reduced this to a linear equation. We have A, just move all your A's to one side. So add 4A to both sides. What would you get? All right, you're adding 4A here. You're adding 4A here. So you get 11A equals what? 220. Divide by 11. A is 20. So what you're saying is that you have 20 adult puppies. Adult puppies. Adult dogs. Adult puppies. You've seen those before. They're kind of weird looking. Little heads, big body. All right, so we know we think we know how many adults there are. How many puppies are there then? 35. And you do that just by coming up here. Puppies is 55 minus A. We think A is 20. So we should have 35 puppies, 20 adults. Puppies is 35. Adults is 20. Yes. Okay. Yes. Okay, so here's the catch on that. That is actually a correct approach. But you got lucky because 11 times 5 gave you 55. Now, what if instead of 55 dogs, it would have been 52 dogs? You could not have done it that way. So it's a good observation, and it works in that case. But with 52 dogs, it wouldn't work that way, right? Because then you would be having to say, okay, 11 times what is 52, and it doesn't go in there nice. And so this is a more of a systematic approach that would work anytime for any amount of dogs. That's right. You could have half, quarter, 3/5 of a cat, dog. All right, I said we're going to take a quiz to start today, just so you finally see what a quiz is going to be like. So if you could, please take out a sheet of paper. Make sure you have your name on it, kind of like we did that one. Your name on the top left. Please kind of spread out so you're not sitting right next to each other on top of each other. Put your name, today's date, and 1314. You can use your calculator, but that's it. There's really nothing else on the quiz that's going to require like a formula like that King, that thing, that steps thing. You don't need that, okay, for this. You ready? Where the heck is it? That's it, those three problems. 23 is what percent of 250? Robert can bike 28 miles in 2.4 hours. How long does it take Robert to ride 100 miles? It cost me $81.21 for dinner last night after tax. So that's the bill that I was given. I left $100. Just left $100 on the table. What percent did I tip the waiter? So, and when I say what percent, I'm saying what percent of the total bill did I tip? All right? Just real quick, pause my video here. Okay, I'll pass that stack around next class then. So what I'm going to do here, I'm not going to go through each of these. I'm going to tell you what the correct answers were, and then either you're going to say, oh yeah, I remember that's what I got, or if you just don't know what to do, I want you to go and try and figure it out yourself. All right, so the first one, what percent? It should be written as a percentage, 9.2%. How long does it take to bike 100 miles? Should be rounded, 8.57 hours. And then the percent for the tip should be 23.15%. So if any of those answers don't look like what you got, please take time to go back and try and rework those. All right? And remember, you can always go back and look at the video to write the problems down again if you need to. All right, so let's do a quick little poll so that I don't have to grade these. No, I still have to grade them. But all right, so the polling is open. How many of you think you got number 1 right? Yes or no? Uh-oh. All right. How many of you think you got number 2 right? Well, that's better. And how about number 3? Really? How do you do number 3? Is it 18? So that's the tip. Then you have to figure out 1820 divided by the original bill. So, yeah, you have to figure out how much the tip was first, and then you say that money, whatever it was, is what percent of 8120. If you do it over 100, then you're doing of the total bill. You don't tip off of what you just tipped off of, right? You tip off of the original. So, okay, well, it is what it is, right? These quizzes are just to kind of keep us honest and humble and be ready for the test. You didn't read it right? How did you interpret it? For what? If you got the tip amount right? Well, it's better than nothing, so, you know, you get a point or two, yeah. Oh, like per hour? Okay, so you did it at a per hour? All right. All right, well, we got to move on. So last class we were discussing What? Yeah, I'll pass that around in a minute. We were discussing, oh, here we go. It was way down here. We'd start doing these scientific notation, engineering notation, decimal notation. Right? Remember these? Okay, so I want to pick up kind of right after where we were talking about that, where it says what is 1. A lot of times in real world situations, I mean honestly, like for math that you actually might see at some point in time, you have to take certain ratios and somehow equate them to some other ratio. Milliliters per hour into liters per day or something, where you have to make unit conversions. And to get started with that, we need to first just be comfortable with basic ratios. Like 1 yard, you want to make a ratio here of 1, what the hell is that? 1 of yards and feet. So what's the relationship between yards and feet? So where are you getting that from? That's right. Now, if you didn't know that, it's up here, right? 1 yard is 3 feet. It's all right in this little table. So I'm going to set up this ratio, and the way I write it is 1 yard per 3 feet. I'm going to say FT for feet. But this is equivalent to saying 3 feet per 1 yard. In other words, your ratio can go both ways. You can have the yards per feet, or you can say feet per yard, and they are the same ratio. How about between meters and inches? Meters to inches. So what do we have up here? Do we have meters and inches here? We do, right? 1 meter is 39.37007 inches. 1 meter. So I'm going to write that ratio down. 1 meter, just put 1m, is 30 what? Point, yeah, I don't remember what it is. 37007. 37007, but you need to put inches. But we could also write that which way? Other way. Now, a lot of times, if we have 1 divided by a number like this, like here we had 1 divided by 3, we could have turned this into a decimal, like 1 divided by 3 on our calculator. Could have been 0.333, and that would have been on top, and on the bottom would have been 1 foot. Here, same thing. We can do 1 divided by this, or just leave it. Doesn't matter. I'm going to just leave it because I don't feel like dealing with a smaller decimal there. Inches and gallons. You can't do that. So we're going to put LNA for not applicable. In other words, you can't convert. There is no ratio that you can set up between inches and gallons, because inches is a measurement of length and gallons is a measurement of volume, and there's not a relationship between those. All right, 21.5 inches is how many centimeters? So watch the way I write this. 21.5 inches, right, is what I start with. Yes? I'm going to put underneath that a 1, just to create a fraction. Then I'm going to multiply by another fraction. And this new fraction is what's going to make this thing turn from inches into centimeters. So in this fraction, what I need is the connection between inches and centimeters. The ratio. So how many inches are in a centimeter, or how many centimeters are in an inch? So do we have a relationship anywhere? All we have here, we have inches to meters, right? And from meters you can go to centimeters, right? So this can be a little bit of a pain, but we'll do it, all right? So first, before I create this fraction over here, I want to know how much 1 inches is. 1 inch is how many centimeters, or how many meters? We just saw it up here, right? 1 inch is 0.0254 meters. 0.0524 meters. 254. So I could say 1 inch. I put the whole word inch instead of just in there, and then I'm going to put 0.0254 m for meters. So I had the relationship, right? I know the relationship between inches and meters. Remember, I want to get to centimeters. What I do is I use this relationship to set up this proportion. Now, why did I put 1 inch on the bottom instead of on the top here? I want cancellation. I want inches to cancel. That is the key when you're doing dimensional analysis, which is what this is. You're trying to get the inches to go away and centimeters to appear. So I first set up this ratio with inches on the bottom, the meters on the top. That way the inch unit will cancel. So cancel the inches out. And now on top, you just have 21.5 times this number. So let's do that. 21.5 times 0.0254. I'm getting, see if you get the same thing, 0.5461. What? What's the unit? Meters over what? What's on the bottom when you multiply across? 1. So you don't really even need it, right? And the inch is gone, right, because it canceled? So what we're saying is that 21.5 inches is equal to 0.5461 meters, but we want it to centimeters now. So how do you go from meters to centimeters? Yeah, that's where you go to this little thing. We're going from meters to centimeters, which is 2 places to the right. We move the decimal point 2 places to the right. It's the same as multiplying by 100. All right? So, but all I'm going to do is just move it because it's a metric unit. So when I move that over, this is equal to 54.61 centimeters. All right, let's try this next one. I want to go from meters to yards, right? 120 meters is how many yards? So I do 120 meters over 1 times, now I need to come in with my proportion that's going to cancel out the meters and create yards, right? So do we have a relationship between yards and meters? Do we know one? Well, they gave it to us right here, don't they? They're telling us 1 yard, that's, we could put a 1 in front. 1 yard is 1.09 meters. So which goes where here? One what on top? 1 yard over 1.09 meters. The meters will cancel. See, if you flip it the other way, the meters don't ever cancel, right? So you have to get the cancellation. And then multiply across. If you multiply straight across the top, you get 120 yards. But then divided by, when you multiply straight across here, it's not 1, it's 1.09. So I actually have to get on my calculator and do 120 divided by 1.09. And I get approximately 110 point, we'll go 0.9 yards. Does this make sense? It's kind of going to be the same thing for each of these. We're trying to go from one unit to the other. We have to find a relationship between the units if possible, and then set up the proportions so that the unit that we don't want anymore cancels. And then we get to something like this. And this can be kind of confusing. All right? So I'm going to try and get us started with this by looking at something else. All right, so what are the units we're looking at here? Inches to centimeters. No, inches squared to centimeters, right? Squared. So when you have a squared unit, that represents area, right, instead of length. So I'm going to start with something I think that'll be a little bit easier to digest, and then we'll move back to that problem. Let's just say I have 1 centimeter here, right? So we're looking at 1 centimeter. It's pretty small, 1 centimeter. How many millimeters are in 1 centimeter? 10. There's 10 millimeters in 1 centimeter. So imagine taking 1, 2, 3, 4, 6, 7, 8, 9, cutting that into 9 dashes, so that's 10 pieces. Each of these pieces, right, is 1 millimeter. So we have the relationship that 1 centimeter is 10 millimeters. Agreed? Now, what is 1 centimeter squared? So visually, isn't that 1 centimeter long, 1 centimeter high, something like that? So imagine measuring out 1 centimeter this way and 1 centimeter up. Question is, how many square millimeters is that? Yeah, so look, if we go 1, 2, 3, 4, 5, 6, 7, 8, 9, that gives us 10 pieces, and then same thing up here, 1, 2, 8, 9. Each of these little squares, right, is 1 millimeter squared, 1 millimeter by 1 millimeter. So there's not just 10 of those boxes in there, there's actually 10 across and 10 up. So you actually have 100 of them in there, don't you? Do y'all see that? Visually, you actually have 100 of these in there. So how in the hell are we going to go from 1 square centimeter equaling 100 square millimeters? When we know for sure 1 centimeter is 10 millimeters, how are we going to know that when you square it becomes 100? I mean, how do we do this? You see what I'm saying? Like, what if it's cubic instead? What if it's 1 centimeter cubed? How many millimeters cubed is it? Is it 10 or 1? Or it's going to be 1,000. But length, width, and height. Yes, so you get another factor of 10 in there. But we want a way it's going to be a little more, I guess, systematic. So look, we start with this base unit, right? And 1 centimeter equals 10 millimeters. What I'd like for you to do is square both sides of the equation to make everything become squared. What happens when you take 1 centimeter, square it, and then when you take 10 millimeters and square it? So let's go through this. 1 squared is what? 1. Centimeters squared is centimeters squared. Same thing over here. 10 squared is 100. And millimeters squared is millimeters squared. Do you see how I'm able to get the correct conversion by understanding what happens to this basic unit and just squaring both sides? Do you see I could do the same thing with cubing on both sides? Yes? If I wanted to know what 1 cubic centimeter was, I would cube both sides of this, and I would get 1,000 cubic millimeters. Okay, with all of that in mind, let's get back to the problem we were just looking at. 1.25 inches squared to centimeters squared. So here's how I'm going to start. I'm going to start just figuring out if I can figure out the relationship between inches and centimeters. What's the relationship between inches and centimeters? So do we have that somewhere? Yeah, we have it. Well, this was to meters, right? We had to go from inches to meters first, and then that we have to go to centimeters. Okay, so make sure we're all on the same page. So inches to meters, we don't have right away. So I'm going to go inches, to centimeters. We don't have. Inches to meters, it was 1 inch was 0.0254 meters. Pardon? It's on our table? Oh, it's down here. 2.54. Well, we were almost there. It's because look, if convert this to meters to centimeters, you move 2 places to the right? So 2.54. So we get that 1 inch is 2.54 centimeters. Y'all with me? Now, I need to get to squared units now. So I'm going to take this, now that I have inches and centimeters, right? And that's what I'm dealing with here. I'm going to square both sides right now. So let's square the left side. What happens when you square the left side? You're just going to get 1 inch squared, or 1 squared inch, right? And over here, 2.54, you have to square it. 6.4516. We'll just go 45. What, centimeters squared? Okay, so everything I've done up to this point is just to get the proportion that I need. Now I'm ready to do this problem doing this little thing here. I'm going to write down what I'm trying to convert. 1.25 inches squared over 1. I'm going to come in with my proportion. What is my proportion? What do I want on top? 6.45 centimeters squared, because I want the inches squared on the bottom so it'll cancel. Over 1 inch squared. Cancel out the inches squared. Multiplying across the top. You have 8.06 approximately centimeters squared, all divided by 1. That's a little involved, right? You have to make sure first you got your inches to centimeters first, then you can square it, then you have your conversion factor right here. If it was squared or cubed, you have to. We're going to get to practice this again on this number 5. This one's a little more straightforward. We're going 55 miles, MI is miles, M is meters. So we have 55 miles over 1. And now I'm hoping that I have a conversion factor miles to meters. Is it given or no? Right there. 1 mile is 1609.344. So what unit goes on top? I want the meters, and on the bottom, the miles. And now just plug in. It was 1 mile was, I already forgot, 1609.344, right? The miles unit cancels. multiply across 55 times 1609.344. I'm getting 88513.92 meters. All right, now we have another problem. This time we have cubic units. Right, when we have cubic units, we need to actually account for the cubes. So let's start by first trying to find a relationship between what two things? Kilometers and meters. Kilometer equals, and then over here, meters. What's the relationship? 1 kilometer is how many meters? 1,000. So you could do that off that table where you drop down from kilometers. You'll drop down, right? Do I need to show it? You know what I'm talking about, the steps. You're going from the kilo down to the universal unit in the middle. So this would be 1,000. And it's probably written down somewhere also, but everyone's okay with that? Now what? Cube both sides. So cube the left, cube the right. The left side becomes just 1 cubic kilometer. The right side becomes 1,000 times 1,000 times 1,000. So I wonder what your calculator is going to tell you. Does yours use the E notation or the times 10 notation, or does it just give you all the zeros? It'll depend on your calculator. It'll depend on your calculator. But let's all understand that whatever the answer you got, it should be a 1 with what, 9 zeros? So a lot of you are probably on your calculator getting like 1E9. We know what that means now, right? Is anyone's calculator in here do the little 10 to the 9 on it? Okay, but no one has it set that way right now? Okay. So this is equal to 1 with 9 zeros, what? Meters cubed. How many is that? It's a billion. It's a billion cubic meters. Now what? Set this up. 16 cubic kilometers over 1. And now come in here with the conversion factor. I want my kilometers to go away. So I put kilometers on the bottom, kilometer cubed, cubic kilometers. 1 on the bottom. And then I put, just for the sake of spacing, I'm going to put 1E9. Because we all understand that that really means 1 with 9 zeros after it now. Equals, now doing that on your calculator, you should get 16 billion. Oh, and those units cancel. 16 with 9 zeros after it. 1.6, yes. Because when you move that decimal over 10 places to the right, the first thing you have to do is get from between the 1 and 6 to the 6, and then after that there's 9 zeros. So that would be correct. And it's the unit, oh, I forgot my unit here, oops, cubic meters. So our answer has cubic meters. So that would work, or 1.6 E10 would work, or 1.6 times 10 to the 10th. Any of those answers would work. Gallons to ounces. Do we have anything that converts gallons to ounces? I hope. Let's see. 1 gallon is 128 fluid ounces. 1 gallon is 128 fluid ounces. So I may be able to do this one without writing it down. Let's see if you follow this. I'm going to write 102 gallons. That's my G's are weird. Over 1. Here's my ratio I'm putting in here, my conversion factor. I need to get rid of the gallons unit, and I need to get ounces up here. The relationship I have is 128 ounces is 1 gallon. My units of gallons would cancel, and I get 13,056 what? Ounces. This one should have been the first one, right? They should have made this the first one. 7 feet is how many inches? But I want to get used to the idea of setting it up. 7 feet over 1. Then I come in with this thing that we're calling the conversion factor. I need to get my feet units to go away. I need to get inches to come back, right? Do you know the relationship between feet and inches? You get 12 inches in 1 foot, right? I mean, a lot of us can say, 7 feet, you just multiply it by 12, and that's how many inches are. But do you see where it's coming from in the conversion factor? All right. So what is it? 84. I'll let you do that one yourself. Number 9. Quinton Quickness can run 12 miles per hour. How many feet can he run per second? All right, so watch the way I'm going to do this. We have not seen one of these yet. He runs 12 miles per hour per 1 hour, right? That's what it means to say he runs 12 miles per hour. We want to convert this over to a new set of units. Instead of miles per hour, we want to look at it in feet per second. So I want you just on the side over here to write feet over second. Put it to the side. This is where we want to get at the end, feet per second, right? So you know how everything I've done up to this point, like all these problems, when I put this number, it was like 102 gallons, and I said put it over 1. This one was 7 feet over 1. Everything we had done, it was always over 1. In this problem, we actually have a secondary unit down there, don't we? We have miles on top. We have hours on the bottom. So to get it to be feet per second, we not only have to make the miles go away and become feet, we have to make the hours go away and become seconds. And it will be opposite of what we did before. Here we wanted miles to go away, so we put the miles on the bottom, didn't we? If we want the hours to go away, we're going to have to put hours on top. And then the other unit of time on the bottom. Do you all see that? It'll be backwards. So the way you approach this is up to you. Let's go after the miles first, okay? I would like to know, do you know a relationship between miles and feet? Yes, it was given to us before. 5,280 feet in a mile. It's up here. Here's a mile. 1 mile is 5,280 feet. I have that conversion factor, so I'm going to start with that here. Here it comes. I'm putting what unit on top? Feet. I'm putting what unit on the bottom? Miles, right? And then remembering that 1 mile is 5,280 feet. That will make my miles go away, won't it? And feet will appear. So I'm happy about that. I'm real happy that miles are gone. Now, I need to take care of the hours on the bottom. And I need to turn it into what? Seconds. Do you know a relationship between hours and seconds? You may not know the relationship between how many seconds are in an hour, but I think a lot of people know that there are 60 minutes in an hour. Would you agree with that? So why don't I do this? I'm going to put hour up here. I'm going to put minutes down here, because I actually know that I think most people know that 1 hour requires 60 minutes, right? That's the relationship. Do you understand what I'm doing? Now, when I do this, my units for hours are going to go away, right? Do you see the hours cancel? But I have minutes here. I don't want minutes. I want seconds. So we're going to do the same process now. You need to come in with another conversion factor that will kill minutes off from the bottom. So the minutes need to be on the top, and you need to somehow connect it to seconds. So you know the relationship between minutes and seconds. 60 seconds in 1 minute. And then I go again and I cancel out the minutes. What's the only unit left on top? The only unit? Feet. And on the bottom, the only unit left is seconds. So this will get you feet per second. All you have to do is multiply all the numbers across the top, and then you come through and multiply all the numbers across the bottom. So do all the top first, do all the bottom, and then divide through and, well, 17.6 feet per second. Now we can write it like this, feet over with a dash second like this. That means feet per second. That's the same as saying 17.6 feet over 1 second or per second. So is 17.6 feet per second fast? It's 12 miles per hour. I don't think anybody runs that fast. Yeah, I do too. I call that BS too. I mean, what is the record? What is the world record for the 100-meter dash? What's the world record? Anyone know? Well, we could look it up real quick. World record, 100 meters. Men's. The current men's world record is 9.58 seconds. Okay, so how fast was he running in miles per hour? Okay, we're going to do this problem on our own. Not on our own. This is just kind of like, yeah, we're just doing it for fun. How fast did he run? He did 9 point, well, it took him 9.58, is that what it was? Seconds to run 100 meters. Yes? I want to know how fast he was going in miles per hour. On average, I mean, because of course he sped up and then, but if 100 meters in 9.58 seconds is equivalent to going how many miles in an hour? So help me out. What do I set up initially as my first proportion? 100 meters over 9.58 seconds. What is my goal to get this in what? Miles per hour. Now, why didn't I do it the other way? Why didn't I put 9.58 seconds on top and 100 meters on bottom? Why not? Correct. I could have set this up either way, but because my final answer is the distance divided by the time, I want my initial setup to also be the distance he ran over time. Understand? Okay, let's try and get this. Let's go for the M first. I want to kill M off and replace it with what? Miles. So do you have a relationship between meters in miles? I'm sure we do. 1609? So 1 meter is this. Are you doing this one right here? Okay, we can use this one, or we can use the other one. Doesn't matter. You want to use the 1609.344? Okay. 1609.344. That's 1 mile. Where'd it go? 1 mile is 1609.344. Yes? Meters. That's going to kill off the meters, and we're going to be happy about that. And make the miles appear. So I'm good with the distance. I just need the time. How many seconds to an hour? So we could do the double thing we just did, or we could now understand that there's a conversion factor that gets you seconds and hours. And that's in 1 hour there are 60 minutes, in each minute there's 60 seconds. 60 times 60 is 3,600. There's 3,600 seconds every hour. My seconds were on top so that they would kill the seconds on the bottom. Multiply across, divide by what you get when you multiply across, and that is going to be your speed in miles per hour. Whew. He's putting Quentin QuickTime or whatever his name was to shame here. Anybody else getting this? .35 miles per hour? But he can only sustain that for 100 meters, you know. If you ask a human being to run a mile, I forget what the record is, world record for a mile, but it's not 23 miles per hour, I can say that. Okay. I hope that that in some way helps you understand what's going on here. Matt fills his bathtub at a rate of 0.4 liters per second. Frank fills his bathtub at a rate of 25 quarts per minute. Which bathtub is filled at a faster rate? I just want to know why Matt and Frank are taking baths. You know, I mean, what's up with, they want a little bit of, what are those, salt crystals? They just want to relax and get away for a while, or what? Calgon, I haven't heard that in a while. Oh, man. All right, so they're both filling up their bathtubs. It's just which one is faster. One of them is given to us in liters per second. The other one, the rate is given in quarts per minute. So we either have to convert the liters per second over to quarts to minute to compare them, or we have to convert the quarts per minute over to liters per second. And it doesn't matter which one you do. So what would you like? You want to go liters per second over to quarts per minute? Try it. We have 0.4 L, capital L, liters per 1 second. I want to eventually turn that into what? Quarts per minute. Let's take care of the time first. Is that all right with you? Can you turn seconds into minutes? Yes. So what unit's going to go on top here? Seconds, because it's on the bottom where we're starting from. And the minutes will go on the bottom. And how many seconds in a minute? 60 seconds in 1 minute. Seconds will cancel and we'll be there. All right, we got to get liters to quarts. Liters to quarts. Liters to quarts. Liter. Nothing. Okay. So if it's not on here, is it? Did we just not do that one? Oh, it's on the homework. What number is it? Oh, there we go. 1 quart, 0.946. So what if you didn't have this? Well, in the real world, we're in the day and age of the computer, right? You just go to the computer, you just go, you could have done this. You could have just typed in exactly 0.04 liters per minute, 2 quarts per whatever, and it would do it for you. But there's our conversion. 1 quart is 0.946 liters. Going the wrong way. Oh my goodness. Where are we? 1 quart. So what unit's going on top here? Quart. And over here, liters. It was 1 quart, so the 1 goes on top, and 0.9 what? 946 liters. Your liters are going to be gone, and then you just multiply. What do you got? 25.3. Is that what you're getting? 3637, what, quarts per minute. And who was this? This was Matt. And what was Frank? 25 quarts per minute, right? So Matt is filling his tub up faster. I did 0.4 times 60. Then I divided by whatever 1 times 1 times 0.946. So Matt wins. All right, there's you got a bunch of homework there. You want to take a little break now? Although that kind of flew by, it was kind of fun. I'm kidding. I'm kidding. All right, let's take a break. 10 minutes. See you back here at 3:21. We have our first test. It's what, Tuesday. It's on a Tuesday, I think. Yeah, the 30th. So we still have a little ways to go. But we're also a little bit behind, so we'll see how things go. I should probably pass this around, huh? Start this here. All right, we're now getting into a new topic. Oh, I was looking at the world record for the mile, and it was done in 3 minutes, 43 seconds, which is about 16 miles per hour. All right, so now we're going to talk about sets, introduction to relations and functions, and then the algebra of functions. So we're finally getting into like algebra material. Everything else has been just kind of a build-up for it to that. All right, so lots of definitions. I think what I'll do is I'll bring up the key to this. we go. Okay, a set is a well-defined collection of objects. An example of a set is a set of real numbers. So all the numbers that we have on the number line is called a set. We can represent that set using the following notation right here. This notation is read the set of elements x such that x is an element of the real numbers. What the hell? Okay, so you start with a brace, and then you're saying, okay, it's all of the x's such that is this bar, such that x belongs to the real numbers. So this little e symbol sideways is element of. So you're saying every x where x lives in the real numbers. Special sets. Here are some special sets. The set containing no elements is called the empty set or null set. It can be written two ways. A set of braces with nothing in it would be the empty set, or I'd shown you before the zero with the line through it is also the empty set. We never write the set with the empty set in it. So we never put a brace around the empty set when we're trying to refer to the empty set. And remember I told you that there's a difference between the empty set and zero? Right? Zero is a number on the number line. The empty set is basically a basket that has nothing in it. If you have a basket that has the number 0 in it, then that's not an empty set. That basket has the number 0. So they're totally different things. All right. The set of all real, the universal set. Okay, a set of objects under consideration is called the universal set, which is denoted with this script U. So if I want to say like the set of all atheists at Northwest Vista College, then U is the atheists at Northwest Vista College. That's my universe. That's my given set, the objects under consideration. The set of all real numbers, everything on the number line, is given the special notation R. Or sometimes you'll see a double struck R. I think I showed you this before. It'll look like this, right? All real numbers. All right, within a set, you can have operations. The major operations on sets are union, intersection, and complement. So when you think union, you think put together, right? If you have two sets, A and B, and you write A with a U between them, B, this is the set that's created when you throw all the elements from both sets into one big bucket. So look at this. We have one set here which contains 0, 2, 4, and 6, another set which contains 2 and 8. The union of those two sets has the 0, has the 2, the 4, the 6, and the 8. Notice that we don't write 2 twice, right? Even though 2 appears in both sets, we only write it one time because the union is just every number that's there thrown in. So if it appears in both sets, it's only written one time. The intersection of two sets is the elements that belong to both sets. So look at this. 0, 2, 4, 6, and 2, 8. What are the elements that belong to both sets? 2. 2 is the only element that belongs to both. How about this one? I'll give you another example here. What if I give you the set 1, 3, 5, and I want the intersection, sorry, my braces look terrible, don't they? 0, 2, 4. And you know what? They don't have to have the same number of elements in them. So what is that? What's the intersection of those two sets? Nothing. How do we say? That's right. This is the empty set. Or you could write So there is no intersection of those two sets. Understand? Okay. All right. Given that a set E is a subset of the universal set U, so what do we mean by subset? You have a set of numbers. A subset is a set that is contained within that bigger set. So look at this right here as an example. Here's a universal set. 0, 1, 2, 3, 4. Those are the only things that belong to the universe, all right? The only things. Then you have A, 0, 2, 4. Do you believe that do you agree that every element in A belongs to U? Like 0 is in U, 2 is in U, 4 is in U. So we would say A is a subset of U. Then the complement of that set is written with a little, what is that? Apostrophe? Is the set of all elements in U that are not in E. So it's everything that's not there. So look at this right here. If A is this, then A complement is everything that's in here that's not in A. So 1 was not in A, right? 3 was not in A. So those are the only things that are in A's complement. Question. What is A union A complement? So you have a universal set, right? Say you're given some universal set, like a script U. You take A, which is a subset of that, and you union it with its complement. What should you get? You should get U. Right? Look at this again. If this is our universe, our universal set, right? A is a subset of that. A complement is everything that's in the universe that's not in A. Then if I put A and its complement together and union them, I should just get back the universal set. What is A intersect A complement? No, A intersect its complement. So what is it? The null set or the empty set. So anytime you try and intersect a set with its complement, it's always going to be the empty set. All right. So here's a universal set. 0, 1, 2, 3, ... means continue this pattern. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 10. A is just 0, 2, 4, 6. B is just 2, 8. And C is 1, 5, 7. First, what's A intersect B? So you're looking at these two. I think I'm going to go to the notes I can write on here. Is that where we are? So A intersect B, we're looking for what these two sets, A and B, have in common. So what do they have in common? Just 2. How about A intersect C? That's this one and this one. What do they have in common? Nothing. So what do I put? 0 with the line through it, the null set. How about A union B? So it's both those together thrown all into a big pot, and you get 0, you've got a 2, you've got a 4, you've got a 6, and you have an 8, don't you? What's A unioned with C? 0, 1, 2, 4, 5, 6, 7. Any questions? What's A complement? So when we look at A complement, we're comparing A to what? The universal set up here. So what is in the universal set that's not here? 1, 3, 5, 7, 8, 9, and 10. 1, 3, 5, 7, 8, 9, and 10. What's C complement? So I'm looking for the things that are in the universal set that are not in C. 0, 2, 3, 4, 6, 8, 9, and 10. Zero, 2, 3, 4, 6, 8, 9, 10. What is A? What? Intersect the universal set. It's just A. Exactly. You could answer as A if you like. Or you could just write down 0, 2, 4, 6 in braces. What's C union U? What is it? Just U. Because U is everything, right? And if C is a subset of U, then if you throw C into U, you already had that, didn't it? Because C came from U, so you should just get U itself. Okay. I really don't like the way that they approach this with all this in here. So I'm not going to go through and fill this in because I just don't like it. I read through it and I'm not happy with it. What I want you to know is that there are two ways in mathematics that we represent sets when it comes to the number line. There's two types of notation we use. We use what's called set builder notation and interval notation. And if you were going to take more math classes, you should be proficient in both and understand both. It's kind of like, I don't know, a long time ago, I don't know if they still do this, but when you would write like an English paper, there was like MLA style, and then there was like some other style, APA, something like that. There's two like styles for referencing. The same kind of thing with this. If you're going to talk about sets of numbers on the number line, there's two accepted mathematical ways of doing it. And you have to know both if you're going to move on and do more math, which you are not. But you should still be familiar with both. So let's just scrap all of this. And look at this chart. And what I'm going to do is I'm going to help you try and understand the notation. All right, this right here is called set builder notation. Set builder. Then these two columns together are where we're going to get the interval notation. So this is basically starting you out by giving you the set notation, and then we need to come up with the interval notation. And we're going to draw a picture to help us. So we are saying here the set, that's what the braces mean, of all x's such that x is, that symbol means greater than 4. X is bigger than 4. So that means that it's all the numbers on the number line that are bigger than 4, but not including 4. If we wanted to include 4, we would put what underneath the equals here? A line, right? So over here on the number line, I'd like you to come over and just mark the number 4 on this number line. And then above the 4, I want you to put an open circle, and then to the right, draw an arrow. So when we write things on a number line, bigger numbers are to the right, correct? Greater is to the right, less than is to the left. So what I want are all the x's. I can pick any value x as long as that value x is bigger than the 4. So it has to be to the right of 4, yes? Now, how do I write this same statement in interval notation? What we do first is we read it like a book from left to right. Do I want anything over here? No, not until I get to where? 4. So I write down the first number that I see, 4. Then I put a comma. Now I write the end of the interval, but it never ends. So we use the infinity symbol. The infinity symbol looks like an 8 that's laying down, going to bed. We put a parenthesis after the infinity, and you always put a parenthesis on infinity no matter what. Always has a parenthesis. And then on the 4, we need to put a symbol in front of it. It's either going to be a parenthesis or a bracket. And that's dictated by whether or not you want to include the 4 or not. If you do not want to include the 4, which we do not here, we put a parenthesis. And that is interval notation. Parenthesis in front of 4 means you're going to start at 4 but don't include 4. And go all the way till you get to infinity. You put a parenthesis on infinity because you can't actually get to infinity. You never can. So I have a daughter, she's 5, about to be 6. And I don't push math on her. You know, she likes math, but I don't like, let's do our math. But I've been trying to get her to understand the idea of infinity, you know, because it talks about how much she loves me and all that. And I tell her, you know, she's like, I love you 100 or something like that. And she tries to quantify how much she loves me. So I've been trying to explain to her infinity, right? And a couple of weeks ago, she's like, Daddy, I have a favorite number. I was like, you know, and I thought she was going to say infinity, you know. And I was like, really? You know, what is it? And she, you know, out of nowhere, she's like, 20. Like, 20? Why? She said, I just really like 20. So I said, I thought you were going to say infinity. And she said to me, she said, infinity is not a number. Because I told her that. Infinity is not a number. Okay? Infinity is an idea. Okay? You don't ever get to, there is no biggest number, right? So you can't call infinity anything tangible. It is purely a concept of going forever in that direction. So that's why we have to put the parenthesis, because the parenthesis means you can't actually achieve it, right? You just keep going. And in the other direction, going from right to left, we put the parenthesis on 4 because we don't want to actually ever get to 4. If we ever get to 4, then we're including 4, and this says we have to be bigger than 4. Understand? All right, how about this one? The set of all x's such that, how do we read this? Negative 1 is less than or equal to x, but that x we also have to have must be less than 4. So it's like the value that you have is smashed between two things, negative 1 and 4, but to include negative 1. So over here on a number line, let's write down negative 1 and let's write down 4. And my x has to live between those two. It can be anything bigger than negative 1, anything less than 4. It can be equal to negative 1, but it cannot be equal to 4. So you notice the usage of the open circle here versus the solid dot. Open circle, I'm saying, look, you can't be 4. You have to be strictly less than 4. Here I put a solid circle, solid dot, because x can actually be negative 1 according to this set notation. So once you kind of have a picture on a number line of what's going on, now you come over here and you read it like from left to right. Where do things start? Where do they end? Negative 1 to 4, right? Can I ever actually be negative 1? Yes, so instead of doing a parenthesis out here, I use a bracket. And then on the 4, can I be 4? No, so parenthesis. See the difference? No, that's a brace. No. Now, look, the brace is reserved for when you have single elements. Like, I'll give you an example underneath this. What if I told you that x could be 2 or 4, but just 2, just 4, nothing between them, nothing outside, just those two numbers? Then you would say brace, 2, 4, and brace. You see the difference? The brace means these are single, we call them singletons, single answers. When you put parentheses and brackets around these things, you're including entire regions of everything in between them also. So that's how you can distinguish between interval notation, single answers, have to have the braces. Does that make sense difference-wise? What about this? X, such that x is an element of all real numbers, which means x can be anything. That means it can be anything you want, both directions forever. So it goes from the left, there is no left, it goes forever. So how do we say that? Negative infinity, negative because it's to the left, then to the right, positive infinity. Parentheses on both, why? Can't ever actually get to them. All right. Find the set of x's such that x is less than 2, intersect the set of x's such that x is bigger than or equal to negative 5 and less than 8. So we're going to try and do this visually. So this first set right here, I'm going to do this one in blue. The second set, I'm going to do it in green. So let's just do the blue one first. I'm going to go to the number 2 on the number line. Just going to make it up. Oh, I better do it in blue. And I want everything, what? Less than 2. Do I want to include 2? No. So I draw open, right? And I draw to the left like this forever. That's the blue set. Now the green set. I've got to be between negative 5 and 8. So I need to put negative 5 and 8 on this number line. And I'm going to do it in green. I just got to make sure they're in the proper order. Negative 5 is to the left of 2, isn't it? And 8's to the right of 2. Don't worry about whether or not you've measured out equally. That's not important. I want everything between those. Do I want negative 5? Yes, so solid. And then do I want 8? No. So I want everything in blue intersecting with everything in green. That means, where do these two sets overlap? What do they have in common? So where do they overlap? Right in here. Right? This one is saying, hey, look, I can be negative 5. The blue one is saying, I can be negative 5, right? The green one is saying, yeah, you can be negative 5. That's what we both have in common. Everything in between here is in common. What about at 2, though? The blue one says no. The green one says yes. To intersect, they both have to say yes. So you want everything up to 2, but not including 2. So let's try and draw the answer down here. I'll do it in black here. Negative 5 to 2. I can have everything between. They both share negative 5 in common. They do not both share 2. Do you see the relationship between these? That's their intersection. What is that answer in interval notation? Bracket negative 5, comma, 2, parenthesis. Negative 5, including negative 5, all the way to 2, don't include 2. That's interval notation. for this, well, the intersection of those two sets, right? The set builder is what's up there. You build the set using those two sets in their intersection. So I'll put this over here. Now, this is where it came from. Can you forget everything that's up here right now and now take this interval and write it as set builder? The set of x such that what? What is this telling you? X must be bigger than or equal to -5 and less than 2. Right? This means I've got to be between these two. So x has to be between -5 and 2. So bigger than -5, less than 2, and I can include -5. Questions? Yeah, I didn't like this either. Function notation. So we got it. Now, I crossed all this out. It doesn't mean that we're not going to talk about it, but we're definitely not going to talk about it the way it's talked about here. Okay, I'm going to talk about it, but I'm going to do my own notes for this. So, a relation. It's exactly what it sounds like it is. A relation is a relationship. Okay, it's a relationship between two quantities. I'll give you an example of a relationship. Now, this is where things can get very confusing in mathematics. We just said that when you write this with two parentheses, right, that we're talking about an interval. Yes? That would mean like everything between 2 and 4. But that also means something else in math, which can be points, which is one thing I really don't like about our notation math, is because there's no way to distinguish between these two unless you know what you're doing. So look at it this way. Do you all remember ever seeing what we call the plane, the flat sheet of paper, and you would label this the x-axis and this the y-axis? Yes, we've all seen this? Okay. If I look at this and call the value that comes in the parentheses first x and the value that comes in the second in the parentheses y, then what I've created is a relation or a relationship between the x and the y. What I'm saying is that when the x value is 2, the y value is 4. When the x value is 3, the y value is 5. When the x value is 4, the y value is 10. So anytime you connect two things together, it's called a relation. So if I were to try and graph these as points, all right, that's the big thing. The first one says that if I go 2 to the right, I should go up 4 and put a dot there, and that would represent that first point. We good with that? The next one would say go what, to the right 3 and go up 5. Put another point. And then the last one says go to the right 4 and put a point way up at 10. And that's all a relation is. It just relates two things together. Now, how is a relationship different than what's called a function? And that's the next thing, the next definition. A function is different than a relation in this respect. For a function, each input, which for us is going to be the x value, must go to one output. Which is the y. The input is called the domain. The output is called the range. So I highlighted here, or underlined, to be a function, each input must go to one output. And also throw one more thing in here. Function is a relation. Every function is a relation, but not every relation is a function. So a function is a special type of relation. It has the property that for each input, for every one of these x's over here, there's only one output. There's only one number that comes out. So let me show you an example, first of all, of a relationship that is not a function, and we'll compare it to one that is. So here's an example of a relation, but not a function. So a relation just connects things together. 1 is related to 5, right? 2 is related to 5. 2 is related to 3. 3 is related to 1. 0 is related to 0. That's a relation. That's all you need for a relation. It's very, very simple. But to be a function, every input, so for us the inputs are this side, everything on this side in, everything on this side out, each input goes to only one output. So where do we run into the problem? 2 goes to 5 and 2 goes to 3. Do you see that? That is not a problem. Okay? So, but that's why I put it there, because I want to make sure you understand the difference. See, look at it this way. 2 goes in, what comes out? 5 and 3. So you see that if you draw a picture, that the 2 actually went to 2 different places? That's what I was saying here. Each input must go to one output. 2 goes to 2 different places, not a function. Now, let me ask you, where did 1 go? 1 went to 5. Let's change something, because this is going to confuse you. You see where it says 3? Make it 5 here, because I'm going to show you. Compare the 1 going to 5 to the 3. Where does the 3 go? 5, right? Does each input go to one output? So did this one go to one place? Did this one go to one place? The fact that they go to the same place doesn't matter. So it almost looks like this if I redraw it. 2 arrows going to 1 is okay. one arrow going, two going to one number, left to right, is not okay. One number going to two, I'm saying this backwards. Sorry, I know I'm confusing you. If you have one number that goes to two places, you fail to be a function. If you have two numbers going to one place, that's okay. You can't. Yes, you can have the same number here going to two different places. Yes. Now, let me give you an example of something that is a function. And of course, if it's a function, it's a relation. Right? Is this a relation? Question. Is that a relation? Yes. Is it a function? Yes. The reason it's a function is because I don't see any of these repeating, right? So there's no way that I'm going to get the same x value going to two different y's, or anywhere. It's not going two different places. So it is a function, yes? What's the domain? All the inputs, right? 1, -4, 0, 2, yes? How do I write that set of numbers? A brace. Let's put them in order. We don't have to, but how about -4, 0, 1, 2? Those are all my inputs. How about the range? What are my outputs? 3, 5, 7. Did y'all notice that 1 went to 3 and 2 went to 3? But that didn't cause us an issue, right? As we'll see later, a function has to follow the property that, what we just said, for each input, it goes to one output. Later on, we'll talk about what's called the inverse of a function. And that means we want to go backwards. And to have an inverse, you cannot have this situation where you have 3 appear twice. But that's later, all right? For now, this is all we're talking about. Domain, range. I believe we can go to the notes now. No, we're not ready to go to the notes. Did I pass it up? No. Yeah, I'm going to have to continue with mine. If x and y are related, then sometimes we can express the relationship explicitly. Let me give you an example, and we'll see if we can come up with a relationship on our own, like the explicit expression of this relationship. Here it is. 1, 2, 2, 4, 3, 6, 4, 8, 5, 10. Can you look at these and first tell me whether or not it's a function? It is a function, right? Because we don't have any inputs repeating. But can you tell me what the relationship is between 1 and 2 and 2 and 4 and 3 and 6 and 4 and 8 and 5 and 10? It looks like it's whatever the input is times 2. Right? Double the input, you get the output. Double the input, you get the output. Double the input, you get the output. So in general, if this is x, what should the next thing be? 2x, right? So I can express it explicitly this way. The y coordinate, or the y value, right, because we said it was x and then y, the y value will always be double the x value. That's the explicit representation of this relationship. If you tell me what the x value is, the input, I should be able to tell you what the output is, right? Yes? Now, if it's a function, which in this case it is, right? If it's a function, then we write this instead. F of x equals 2x. That's the way we say that. F of x is how you say this. So let me just try and explain what the whole difference is between writing this and this. If you write y equals 2x, it establishes a relationship between y and x. But if you write f of x equals 2x, you're telling the person who's looking at this that you're guaranteeing them that every input goes to exactly one output, that they don't have to check it themselves. That's what's happening. So it gives them a stronger condition than just a relationship. So anytime we have a function, we write it this way. Here are some examples of functions. F of x equals 2x plus 4. That's very similar to the function we just had. It takes the input, it doubles it, but on top of that, it does what? It adds 4. And that's what the y value will turn out to be. So let me show you, if I plug in 1 to this, what is this thing going to do? 2 times 1 is 2, plus 4 is 6. If I plug in 2 to this, it's going to do 2 times 2, which is 4, plus 4 is 8. And so you can tell from here, from the one over here, it's not the same, right? It's not the same function. Now, another way of writing this, if I want to tell you plug in 1 or plug in 2, I could write it with this alternate notation. I write f of 1. So I put 1 like this. What does f of 1 mean? It means rewrite this, replacing x with 1. So you get 2 times 1 plus 4, which is, what did we say? 6. So look, there's something subtle happening here. This is the input, right? This is the output. Input, output. When you write f of 1, you are saying what is the output of the function when you plug 1 in. Because look, the answer is 6, right? The answer is not a pair of numbers. It's just the y value. So f of 1 is the output after you plug 1 in. Here I'd write f of 2. This would be 2 times 2 plus 4, which we said was 8. Again, it's the output that you get when you plug 2 in. Now I could do this all day, right? I could get another set of numbers that would work in here. Trying, let's do what? 3 would give you, let's do it mentally. 6, 10? Yes? Okay. Now if I do this, do hundreds, thousands of these, then what I could then do is start drawing all the relations on a graph. I could put x here, put y here, and I could start putting all these on here. Like 1, 6 would mean go to the right 1 and up 6. So maybe I do something like this. Then 2, 8 would put me up there. 3, 10 would put me up here. And if I did all of them, filling in every little space, I would get a picture, wouldn't I? And that would be, in this case, a line. And this right here is called the graph of the function. And I'll call it graph of f, because f is actually the name of the function here. F of x is the value of the function at x. There's a difference between the two. The value of the function at x is going to be a y value. F itself is just the name of the function. So this would look like a line. Do all functions look like lines? No. If I threw a squared on here, 2x squared, now I'm going to create this thing called a parabola. And if I put cubed on there, it's going to be cubic. And if I put a square root in here, it's going to be a square root function. There's a bunch of different ones. Absolute value. But the idea is that a function should have a picture that goes with it. All right, let's see if we can get back to this thing now. I think that might be enough for us to pick up on this. So here's an equation, y equals 9x minus 5. But if I rewrite that same equation in functional notation, f of x equals 9x minus 5, then I'm just reading through this here. What the heck? F of x is the y value at x. Forget what they have in here, okay? F of x is the y value at x. You plug x in, it's the y value, right? It's specifically exactly the y value that comes out when you plug x in. X is the input, right? Y and f of x are the same thing, all right? They are the same thing. They are equal. You can fill that in. Y is equal to f of x. F is the name of the function. I'll show you a function. Time, bored. When you walk into this class, the very beginning, you're already kind of bored. But as time goes on, we get later and later into this class, your boredom increases. And sometimes it goes real quick and you just, all of a sudden you fall off the boat and then you just get really bored. And then you get to this maximum boredness maybe, where you're just totally checked out and you're just like, you know, you've hit the peak of being bored, right? That would be a function. It relates the time, how many minutes have passed, to basically how much you're paying attention in here or something like that. Something as simple as that can be modeled like a function. So we could call this, if we wanted to, B. We could call it B of t, where B is the name of the function, and it stands for bored. It's the bored function, right? The B is the name of the function. B of t is how bored you are at exactly time t. You see the difference between the two things? A lot of people think that the name of this function is B of t. It's not. It's B. And if you wanted to really be clear about it, you could write bored of t. And there, it's explicit. But we like to write f of t or f of x to represent f for function. Now, we were just kidding, right? When you come in here, you're super bored, and as time goes on, you get to this where you're just like not even bored anymore. Everything is fun. So we could graph the fun, exciting function. I'm trying. Look, you have to try and find any glimpse of any humor, even if it's not good. You have to pull it in and try and, you know, just try. All right, so here's our function. We're going to say evaluate How do you say this? F of negative 3. All that means is replace x in here with negative 3. Are you given the input or the output right now? Input. What's the answer? 9 times negative 3 minus 5. Negative 27, take away 5 is negative 32. Evaluate f of 4. Are you given the input or the output? Input. What is it? So 9 times 4 minus 5, 36 minus 5, 31. Find x if you're given f of x equals 85. You're given the output this time. In other words, you're given the y value, aren't you? That's the y value is 85. So what you want to know is what x do you plug in to get 85? So I'm going to write down this. 9x take away 5. I have to plug some x in there to get 85 out. Right? 85 is what comes out when I plug in x, but I don't know what that is. Solve for x. It's just a linear equation. So add 5 to both sides, and then divide both sides by 9, and you get x is 10. And you could check it. You could just plug 10 in and just verify that when you plug 10 in right there, you get 85, which you do. Evaluate f of a. What are you given? Input. The problem is it's not a number, right? It's not a specific value. So that means I'm just going to rewrite the function, replacing x with a, and you can't do anything to that because you don't know what a is, right? So you just leave it and box it. It's kind of weird. When someone defines a function and then tells you to plug in a letter, you just go in and replace all the letters x with whatever the letter was, a. That really doesn't make a whole lot of sense why you'd ever want to do that, right? Like, why would you ever want to plug a letter into a function? Believe it or not, it has a lot of value. So let's see what the next one is. F of a plus 2, are you given the input or the output? Input. The input, and what is the input? A plus 2. I haven't been writing them down, but that means I'm going to go in here and I'm going to replace x with, okay, okay, so that's what I was going to ask you. If I'm going to replace the x with a plus 2, there it is. If that 9 is supposed to multiply times the entire x. So it's got to multiply times the entire a plus 2. If you miss that, it's going to be completely wrong. Now the most you can do is just clean this up. Distribute the 9 through, collect like terms. 9a plus 18 minus 5, so 9a plus 13. Big difference between the two, right? What is one of the biggest mistakes I see whenever people are asked to do this? They write down this. They say, oh, I'm going to replace replace x with a, and then I'm going to add 2. Right? F of a plus 2, they replace the x with a, then they add 2. That's not even close to being the same thing, is it? And this is completely wrong. So don't be the one who does that. I mean, you wouldn't be the first, but I'm just saying, like, that's the biggest mistake I see. People lose sight of where that a plus 2 is going. All right, now we get into some more complicated looking functions. What's the name of this function? P. It's P of x equals 4x squared minus x minus 4. So now we have a little more complicated thing happening here. Let's find P of 2. So they're asking us to find this. So P of 2, everywhere you see an x, put a 2. I just wrote everything down, okay? But I need to get a little bit better with my parentheses maybe here. This x squared means I have to square this 2, right? So it might be worth it for me to put that 2 in parentheses. Should I first do 4 times 2? No, because order of operations says exponents first. So square the 2 first, which is 4, then times 4, 16. So I've got 16 out here, minus 2 minus 4 is 10. Questions? What? Where? Yeah, this should have been written, find P of 2. It's just bad writing here. It says evaluate the following functions at the indicated variable. They should have separated these somehow to let you know that that's where they want you to plug. That's what they want you to plug in. Yeah. We're finding P of 2. That's what I put here. Yes. So P of 2 equals this, which equals this, which equals 10. Oh yeah, yeah. No. This is the function. This is what they wanted you to find right here. Find that. Same thing on this one. They give you the function, and then they want you to find P of 1/2. That means I'm going to replace every x with 1/2. 4 times, I'm going to use parentheses, 1/2 squared minus 1/2 minus 4. Should I have put parentheses around the 1/2 right here? See on that one, the x, did I need it? I didn't need it. I mean, would it hurt to put it? No, but you don't need it. Now, you have to have the 1/2 here in parentheses because you need to make sure that you're going to square it first, not multiply these. So what's 1/2 squared? 1/4. So this is really 4 times 1/4 minus 1/2 minus 4. 4 times 1/4? 1. 1 minus 1/2 minus 4. What's 1 take away 1/2? So negative 1/2, or no, sorry, 1/2 minus 4. I just did these two in my head. 1 take away 1/2 is 1/2. And then you have 1/2 minus 4. Getting a common denominator. I rewrite 4 as 8 over 2. So now subtract 1 take away 8 is negative 7 over 2. Negative 7/2. I know someone's going to ask, if we put negative 3.5, is that okay? I don't have a problem with you putting negative 3.5 as long as your work on your test doesn't look like this. Like none of this is here, and you just put negative 3.5. That I won't accept, because on your test I will say, show all work to receive full credit, which means you have to show me you know what's going on here. It can't just be, where is it? It can't just be that. Where? Mm-hmm. Then show me what 0.5 squared is. I know, but you would write it down there in times 4. Well, here's the thing. If you get this wrong because you typed something in incorrectly and you show no work, you get nothing. Well, then that's a chance you're willing to take, but if you type it incorrectly and you get it right, you should get the point, no? That's an argument. I'm telling you, you have to show your work. So here's the thing. I mean, I haven't met many students, okay, that are proficient enough with their calculators that they don't make the mistakes of where to put the parentheses and everything like that, and they'll get them wrong, no work, and it's no credit. You know, it's all wrong. So you need to show your work. That's my expectation. What's the difference between this one and this one? The negative 1/2. So how does that impact things we plug in here? We have 4 negative 1/2 squared minus what? Negative 1/2? Maybe I should put parentheses then, because it doesn't make a whole lot of sense to write minus minus. You should put it in parentheses. Then minus 4. So there's a slight difference between this one and the one before. When I square this, what's negative 1/2 squared? It's still positive 1/4. So that's going to become 4 times positive 1/4, but this one's going to change, isn't it? Minus minus is plus, and then minus 4. Order of operations, 4 times 1/4 comes next, so that's 1 plus 1/2 minus 1/4. What's 1 plus 1/2? 1.5 or 3/2. Common denominator, put those two together. Take away 4. What's 4 is a fraction, rewritten as a fraction with a 2 on the bottom? 8 over 2. What's 3 minus 8? Negative 5 over 2. All right. Let's see, how much more do we have here? Is this... Just looking at this, I'm looking at time here. Still got a ways to go here. I'm going to give you a little challenge problem for you. All right. So I want everyone to take out a sheet of paper. This isn't a quiz, all right? I'm not going to grade you on this, but I want a response from everyone. You're allowed to use your calculator, all right? Okay. Go ahead. I want to see, for those of you who would want to use your calculator, I want to see if you can get this with your calculator. All right, so I want to see if you're comfortable with it. That way, when I'm grading, I can be like, okay, they're getting the answer. I know that they're using their calculator. Cool, that's all right with me. When you have an answer, please press your little yes thing on your... So when you have both answers, press Number 1 on your voting thing. $14. Did everyone press yes when they're done? We're waiting on a few more. No. 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 I have to go back and look at the syllabus for the homework, but like what it is, but we'll deal with that later. Okay, I think that's good. All right, now we're going to vote again. Anybody want to share their answer for number 1? -3? Okay, yes or no for -3 for number 1? Yes or no? Don't be afraid to vote because I'm not going to call you out. Like, who said no? Who said yes? All right. We done? No changing your mind now. Everyone good? All right. That is the correct answer. That is the correct answer. And look, so look at 75%. So that's a quarter of you that didn't get it right. And I'm not quite sure if the quarter is by hand or by calculator. I don't know. But that's enough for me to be concerned about the reliability of the calculator to get the correct answer. This should be -1 squared minus 1 minus 1 cubed. Now we'll get back. I'm going to come back to that. Let's look at the second one. Anyone want to volunteer their answer for this? 1? Yes or no? Everyone done? So how is it 1? You got 3? On the calculator by hand? You wrote it out? All right, so let's look at this one. When you have a negative in front of x squared right here, that really means -1 times x squared. The negative is not being squared, only the x. So this should turn into -1 times, now let me replace the x with -1. -1 squared. Then I have minus, so here's minus, and what am I subtracting? -1, so I put -1 in there again. And then I have minus, and then I have in parentheses -1 cubed. Exponents first. What's negative 1 squared? Positive 1. So my first one is negative 1 times positive 1. Then what's minus negative? Plus 1. And then I have minus here. And then what's negative 1 times negative 1 times negative 1? Negative 1. So multiplication, negative 1 times negative 1 times 1 is negative 1, then plus 1, and then minus a negative is plus. So you get negative 1 and 1 together, 0 plus 1, or you could say 2 minus 1, 1. So the correct answer was 1 for the second one. This was correct for the first one. So I'm just, yeah, y'all go ahead. Just got to be real careful with the calculator, and that's the only thing I'm concerned about.